We are now to angular momentum, which is perhaps my favorite topic from this chapter, and in a way the most important topic from this chapter. Now, we're going to start with the definition of angular momentum that is valid for particles only, and later we'll generalize it for extended objects. So L is the symbol for angular momentum, and this can be written as mass times radius times speed sine beta, where beta is the angle between the radial vector pointing from the origin to your particle, the angle between that and the momentum vector. Now note that the definition is actually coming from cross products, but it's okay to just use this equation if you understand what beta represents, the angle between these two. So this is just like momentum, except it's the rotational one. So that's where the extra factor of radius comes in, the distance we are from the point that we're considering the rotation around. So keep in mind that every rotational quantity up till now, we've always had an axis or a rotational point defined. Same thing for this. In this picture, it's the origin. This starts to make a little more sense when we think about circular motion. Imagine I have a point going around in a circle, which goes around the origin. In this case, we again have MRV sine beta, but in this case beta is 90. Sine of 90 is 1. So angular momentum is now just m times the radius it's going times the tangential speed. If this is uniform circular motion, that's constant. Now we can use the right-hand rule and see that because I'm saying r cross, right, r cross P is your angular momentum. Start with your fingers pointed along R, so pointed like, what is that, 1:30 o'clock, and then turn your fingers towards V. Your thumb is then pointed at you out of the page, which we would call the positive Z hat direction. So that's why we would say that this is angular momentum sub Z, the Z component of angular momentum. So this is a situation where it makes a little more sense to talk about the angular momentum of a particle. If your particle is going in a straight line, angular momentum is a little less meaningful. I haven't yet told you why you want to care about angular momentum, and that's going to be in the next video, that the idea is that this is a quantity that is conserved. So that's why we're going to actually need to calculate this. Now, a different definition of angular momentum is for a rigid object, that in this case, our angular momentum is equal to the moment of inertia times the angular speed. And again, we can say that this is analogous to a linear motion equation that you know. Now, the caveat is that the direction here is that vector direction, which you can get from the right-hand rule. So based on how this wheel is spinning, you would make your fingers rotate with the wheel, your thumb points in this direction, and so your angular momentum has the same direction as angular speed. Now there is a caveat. This is not actually true in every single situation. This is true in certain situations. However, those are the only situations that we're going to deal with. So I only say this because if you start Google searching angular momentum rigid objects, you might find some crazy stuff dealing with tensors. We're not doing any of this. So we're only going to consider simple cases where this is true, but if you go out on the internet, you can find some crazy situations we're not dealing with. Lastly, torques change angular momentum. So when you have a net torque, that is your change in angular momentum with time. If your torque is constant, then you have a delta L over delta T. And again, this should resemble, or you should remember, that this looks like a linear equation, which was F net. Now there's two situations we would think about. One is simply changing the direction without changing the magnitude. That's really hard. That's actually section 12 dealing with gyroscopes, and we are not worrying about that. That's really hard to think through. So the second situation, which is easier to think about, is saying that the direction is the same and we're only changing the magnitude. Well, remember that our angular momentum is equal to our moment of inertia times our angular speed. So if this is changing, then our angular momentum also must be changing. But we've said that our net torque, if you then multiply this by moment of inertia, you get alpha. So actually, if we divide both of these sides by I, moment of inertia, we just come back to this equation. So, right, that's all that's going on. So let's think about this. Let's say that I have a wheel that is spinning at angular momentum omega. Sorry, angular speed omega. It has some moment of inertia, right? We then apply a brake, right? This is now going to be a frictional force, and it's going to be slowing the wheel down. Note that this is a torque because there's some axial distance between this. So what we get now is that the wheel is slowing down. Because we've applied a force, so we then have an angular acceleration, which is opposing our angular speed. But we could also think about this just in terms of decreasing our angular momentum because we're decreasing our angular speed, right? So we have a torque here. So that's really just one way to think about this, is that we can think about this as angular momentum and torque, or we can think about this as angular acceleration and angular speed. It's all related.